In this video, we're going to talk about endowment effect, framing, and loss aversion. And in a minute, we'll see that they actually can be integrated into one framework, kind of. So let's first consider two games. Game one is that you have two choices. Either you lose $300 for sure, or choice B, we toss a coin. If it turns up head, you lose $600, and if it turns up tail, we break even, so you don't lose anything. So pause for a minute and think which one you choose. Now let's look at game two. You still have two choices. First choice is that you can have a bank balance of $26,230 for sure, or you can have a bank balance of $25,930 if we toss a coin and it comes up head, and $26,530 if it comes up tail. And also pause a minute to see which one you will choose. So if you're normal people, you probably will choose B in game one, and you will choose A in game two. Okay, and now we are going to explain why this is troublesome in from the view of the traditional expected utility framework. Now, to make things a little bit easier, let's, for now, assume that the agent is risk neutral. Okay, so what is expected utility here? The expected utility is for A is negative 300, and for B, because we have risk neutral, it is 600 times 0.05 plus 0 times 0.05, which is 300. So in game one, it should be equivalent between A and B if you are risk neutral. Now let's think about game two. Okay, so if you realize that if I subtract this value from these two values, and this is exactly lose $300, and this is exactly lose $600. So the expected utility here is something like C negative 300, and expected utility here is something like C minus 600 times 0.05 plus C times 0.05, which is C minus 300. So still, they should be equivalent. So if you assuming risk neutral, then you would have the agent choose should be evenly split between A and B. But that is not the case. So that can be explained by the expected utility framework. So now let's see how loss aversion actually solve this problem. Let's have another version. Let's use the prospect theory, and let's do a graph. So we already know that let's say this is your payment, and this is your utility. It's a plus. So our risk neutral agent, his utility would look like something like this. So you have a symmetry between positive and negative. So it actually didn't matter to you whether or not you win a little bit or you win a lot more. Or you win a little bit or you win a lot more, because their middle point will be exactly lying on the line. What prospect theory propose is that actually you have asymmetry utility function. So it looks like something like this. Now if I have a unit of loss here, I'm tremendously worse off. But if I have same amount of unit gain here, I only get better a little bit. So the positive utility associated with gain is disproportionate with the negative utility associated with loss. And that is why people are afraid of loss way much more than they want to keep their gains. And that explains why when you're facing a potential loss, you would like to take a very risky gamble because you have this option that you can break even. And here, because the illusion of gain, and especially the gain is very large, so you can think that this is actually extended to a very flat region, you would much rather keep the gain you have than take a gamble that potentially you can lose a lot. So, or the alternative way would say is that the extra gain is not that attractive to you. So that is a prospect theory. Now there are 2 points I want to make here. First is that why this has anything to do with framing. Okay, it has something to do with framing exactly because prospect theory told you that your loss and the gain have asymmetry utility. But how do you define loss? Where is the reference point? Okay, where is your ground zero? So that is where the framing comes in. Is we can question a frame in such a way that they affect how you define your endowment. So that is association of the endowment effect and the framing. So, which is framing gives you the reference point or gives you the endowment. Okay. The second point I want to make is that loss aversion is not equivalent to risk aversion. Risk aversion is saying that if you got a really concave function, a concave utility function, and you got 2 choices. The certainty choice, let's say this is the certainty choice. The utility of the certainty choice is larger than the expected utility of the risky choice. Because expected utility of the risky choice, let's say half-half, will be somewhere on the line that crosses these two. So this delta is why you have risk averse. Okay, this is not the same as you have asymmetry utility for loss and for gain. Okay, and if we use loss aversion, we use risk aversion to explain the story, it does not go through either, because if you are risk averse, then you should choose A for 2 games rather than switching from B to A, because the first choice gives you much more certainty than second choice, for sure. So although we made an assumption of risk neutral here, this is purely for the sake of demonstration. You can actually work out a problem that has risk averse agent, and the same conclusion will go through.